All right, let's just jump right into it. We are going to tackle one of the biggest questions you could possibly ask. A question that takes us all the way back to the very first instant of, well, everything. What in the world happened at time zero?
Think about it. We're basically cosmic detectives. Our mission is to understand the origin story of our entire universe, to somehow peel back 13.8 billion years of history and try to get a glimpse of the moment it all kicked off. So how do we even start to figure this out? Well, cosmologists do this incredible thing. They take our whole expanding universe with all the galaxies flying apart from each other, and they basically just hit rewind. And as they do, everything rushes back together, getting hotter, getting denser, until the entire cosmic movie rewinds back to a single, powerful first frame.
And that first frame, that's what we're calling time zero. Our best calculations put it at about 13.8 billion years in the past. It's the theoretical starting line for space, for time, for all of it. And this starting point has a name, the initial singularity. It's this core idea in cosmology that describes a state that is, well, it's almost impossible to imagine. It's a single point where all the stuff of the universe was crushed together, right before that great expansion we all know as the Big Bang.
Okay, so we've got this word, singularity. But what does that actually mean? You know, in physics, a singularity is kind of like a big red flag. It's a point where the math just completely goes haywire, and things like density and temperature shoot off to infinity. It's basically the math telling us our theories have hit a wall. To really get a feel for how extreme this is, let's just try to build this picture together, step by step. First, just imagine everything. Every single star, every galaxy, all the dark matter, all the energy, all of it. Now imagine taking all of that and squishing it down into a space with zero physical size. That gets you to a state of infinite density, where the very idea of space just doesn't really apply yet. And to top it all off, let's just crank the heat up to infinity. We're talking so hot, so incredibly energetic, that not even the most fundamental particles could hold together. This is the absolutely mind-bending scene that our classical theories paint for us.
And this is a really, really important point. The singularity wasn't some kind of firecracker going off in space. It was the birth of space and time themselves. There was no outside for it to explode into. Wild, right?
Now, I know this all sounds like something straight out of science fiction, but the thing is, this whole idea of a singularity, it's actually built on some really solid, real-world evidence. We found cosmic clues, these echoes from the very beginning that all seem to point back to this super hot, super dense origin. You can almost see the pieces falling into place over time. It really kicked off back in 1929 when Edwin Hubble figured out the universe is expanding. I mean, if it's expanding now, it must have been smaller in the past, right? Then you fast forward to the 1960s, and brilliant minds like Stephen Hawking and Roger Penrose showed mathematically that if general relativity is right, you rewind the clock and you have to hit a singularity. And then, the real clincher, the smoking gun, came in 1964 with the discovery of the cosmic microwave background, the actual leftover heat from that primordial fireball.
And check this out, this is another huge piece of the puzzle. The Big Bang Theory makes a very specific prediction. It says that in the first few minutes, the universe was like a giant nuclear furnace that should have cooked up about 75% hydrogen and 25% helium. And what do we find when we look out at the oldest things in the cosmos? Yep, the numbers are a perfect match. It's just spot on. So the evidence looks pretty good, right? Case closed? Well, not so fast. Here's where the story gets really interesting. That whole idea of infinity that the singularity is built on, turns out it's also its biggest weakness. You've got to ask the question, does infinity actually exist in the real world? Physicists get really, really nervous when infinities pop up in their equations. It usually doesn't mean that reality is infinite. It's usually a giant sign that says, hey, your theory's broken, you're missing something.
And this is really the central battle in modern physics. On one side, you've got Einstein's general relativity, our theory for the really big stuff like stars and galaxies, and it predicts a true singularity where everything just breaks. But on the other side, you've got quantum mechanics, our theory for the super tiny stuff, which basically insists that physics should never break down, that new rules must take over at those scales. So this big disagreement has kicked off this amazing hunt for a new theory, a new way to understand our origins. We're looking for something that can go beyond the singularity and tell us what might have actually been going on in those very first moments. And this has led to some really mind-bending ideas, even if we can't prove them yet.
The Holy Grail is a theory of quantum gravity that can finally unite those two warring ideas. Some theories imagine a quantum bounce, where our universe didn't start from scratch but actually emerged from a previous collapsing one. A huge one is cosmic inflation theory, which suggests that a split second after the beginning, the universe expanded faster than the speed of light, smoothing everything out and avoiding a true singularity altogether.
So what does this all boil down to? Well, the way scientists think about this is changing. The initial singularity isn't really seen as a literal thing that happened anymore. It's more like a signpost at the edge of a map, telling us, here's the edge of what we know. Beyond this point, new physics is required.
And the cool thing is, we're not just guessing. We are actively out there hunting for clues that could lead to that new physics. We've got incredible tools, like the James Webb Space Telescope, peering farther back in time than we ever could before. And our gravitational wave detectors are like ears to the cosmos, listening for the faintest rumbles from the universe's birth.
And all of this leaves us with one last absolutely profound thought. If the universe didn't begin from an infinitely small point, if maybe it bounced from a previous existence, or it's part of some larger eternal process, then was there ever really a beginning at all? The answer is still out there, waiting for us in the cosmos.